Okay, so okay. Good afternoon, one and all. Welcome to UL Space Club webinar session 53. We are on the 53rd session of our prestigious program, UL Space Club webinar series. When the whole world was stuck due to the COVID pandemic issues, we started thinking about some sort of another activity, and we started thinking about a webinar series. We just started it for 5 to 6 sessions, but the enthusiasm and the response from the students were amazing, and we continued to conduct several sessions based on STEMs: science, technology, engineering, mathematics, and space. So now we are moving on to the 53rd session with an interesting topic related to particles of space-time. So today we have a expert from CUSAT, Dr. Titus sir, and our mentor Shadi sir is here to introduce him in detail, and I'm not going into that. But before going to our webinar session, I have few instructions for the student participants. I request all of you to switch off your mic and camera throughout the meeting unless you are asked to switch on it. When you are asking a question in the question answer session time, you can switch on your mic and camera and ask the question directly. Otherwise, please try to switch off your mic and camera. And you can type your question in the chat window. In Google Meet, there is a special chat window is there. Use the chat window for typing your questions. You can ask relevant questions related to the topic. You will collect the question for the question answer session, and you can ask the question directly at that time. And another important thing is, please don't try to share your screen. Our speaker will share his screen. He will be having a presentation. So when he is having his presentation, don't try to share your screen. It will be an interruption to other participants when they are listening to uh, the speaker's presentation. So please don't try to do that. That are the major instructions we have. And I would like to announce one more thing, that we will have a quiz competition based on this particular topic after the session. So we will announce, we will provide you the link to access the quiz competition at the end of this program. So that's the instruction for the students. So once again, welcome to everyone. Welcome to World Space Club webinar 53. I would like to hand over the mic to Sheli sir to introduce our honorable speaker. Sheli sir.
Okay. Thank you, Varun. We have been sitting here in the 52nd webinar session. We have started there in the midst of this, the beginning of this pandemic, and still we are continuing. And it's become an icon for us to proliferate all over this country and most of the people, and we are making a live streaming of this our program continuously in our YouTube channel, Your Space Club. So we are so happy to be here to have the lecture from Dr. Titus K. Mathew from CUSAT, and he's speaking on the topic Padmanabhan and atoms of space time. The topic itself is a little bit interesting for the Keralites because it's about, I think it's about Dr. Thanu Padmanabhan and its findings, and our speaker is closely associated with that genius of India. So let me introduce Dr. Titus K. Mathew for all of us, and he's a professor from Department of Physics. Now he presently is the HOD of the Department of Physics in CUSAT, and he did his PhD from in physics in the CUSAT itself and MSc also, and he's the head of department from the year of 2019, and he's professor from the year 2014 here, and he is presently is in professional service as a PhD examiner in MG University, Kottayam, and IIEST, Shibpur, Howrah, West Bengal, and reviewer of research articles, and associate editor to international journals, Modern Physics Letters, International Journal of Modern Physics, D. Canadian Journal of Physics, and President Academy of Physics, Teachers, Kerala, and he has produced around 3 PhDs under his guidance, and still he is serving there. And he's a visiting positions and collaborations in the Ayuka, Pune, and visiting collaborator in Fermi National Accelerator Laboratory, USA, and member of ISDT International Science Development Team, Hawaii Telescope Center, USA. And is also selected for some other professional activities as a coordinator of IUCA Center for Astronomy Research and Development, ICARD, Department of Physics, Cochin University of Science and Technology, Kochi, India, and Honorable Director, Center of Particle Physics, CUSAT, Honorable Director and Inter-University Center for Studies in Kerala, Legacy of Astronomy and Mathematics, and is a coordinator of National Workshop on Recent Trends in Theoretical Physics and National Workshop on Current Trends in Applied Physics in 2014, and member of ISD, TMT, Hawaii, USA, and coordinator of the workshop on statistical analysis cosmology in the Department of Physics in association with IUCA Pune in 2017, and the honorary director, Center of Particle Physics, Department of Physics, Cochin University, and regional convener, Theoretical Physics Seminar Certificate Program, Department of Physics, Cochin University, and coordinator of workshops in emergent gravity paradigm. Also is engaged with a lot of activities, and he has already published 50 research publications in several international journals. And so we are so happy to have Dr. Titus K. Mathew with us, and he will deliver a speech, wonderful speech on the origin of our space and even the universe, and about the great Indian scientist of Dr. Thanu Padmanabhan, who demised last year. So I welcome all of you to receive this wonderful session from Dr. Titus K. Mathew. And with us, we have E.K. Kutisar, the former director, ISRO, is the founder of our UL Space Club. And we have PJ Bhatt sir, he is also from a veteran scientist from ISRO, and Dr. Sundaramurthy sir. And we have several scientists and students who will yet to join with us. And a lot of people are watching this program through our YouTube channel, and our student coordinator already stated there will be a quiz after our program regarding the speech. And I invite, with all respect, our honorable guest, Dr. Titus K. Mathew, to deliver his speech. Welcome, sir.
ഞാൻ audible അല്ലേ?
Yes, sir. Yes, sir.
Yes, sir. So I can speak in Malayalam, correct?
Okay, sir. Some
Or is there any persons who can't understand Malayalam?
few of them are there, sir.
There may be few. There may be few.
Okay.
But you can have a mixture, no problem.
What I want to say is that I have prepared some slides that is in Malayalam.
That is okay.
That doesn't
no
matter,
problem.
right? Okay. Fine. So let me thank first the UL Space Club and the organizers, especially those who introduced me in today's sessions, Mr. Shajil and Mr. Varun. And I'm happy to see that activities like this is centered about a space club in Kozhikode. And it is and I come to know that this is some 50 seconds webinar, I think, if I'm correct. So in that sense, it is a great service to science in general and also basic science in particular. So without going anything further regarding this, let me go on to my topic. So I will share my slide, but here and there at some times I may withdraw the slide and I will present myself in talking. Okay. So I didn't know that there are persons who can't understand Malayalam. That is the reason why I should prepare the slides in Malayalam. Anyway. Is my slide is visible? Okay. It's funny, right? Okay. So as the person who introduced me mentioned, This is about the contribution of Professor Padmanabhan, who was a well-known theoretical physics across the globe and who died unexpectedly 1 year before on September 17. And it was a real shock that he was just went into the screen, behind the living screen, at an age of around 64, I think. So considered to the present conditions, that is not the age to go away from our world, especially a scientist like Professor Padmanabhan. But however, he made some remarkable contributions or some revolutionary contributions to basic science, especially to understand gravity and in some way to understand our cosmos itself. So in that sense, I may say that it is one of the revolutionary ideas regarding gravity, maybe after Isaac Newton and Albert Einstein, because we know these two are the persons who put forward the theories of gravity, or particularly the law of gravity, first by Newton and second by Einstein. Maybe you can take the third contributions in making a fresh law to understand gravity is from Professor Padmanabhan. But the unfortunate thing is that during the completion of this magnificent theory, he passed away. So it is still there for its completions, but the ideas put forward by him is so profounding, and it is still surviving. Maybe tomorrow sometimes, maybe our children will come to know about the theories of Padmanabhan on gravity, which completely redefined gravity in a different perspective. The title of my talk, today's talk, is, I have chosen it as Padmanabhan and the Atoms of Space-Time. So when we are hearing about the phrase atoms of space-time, or say mere atoms, we all know that all materials that we know are composed of microscopic constituents, either atoms or molecules. Say, for example, water is made up of water molecules, and every water molecule consists of 2 hydrogen atoms and an oxygen atoms. Likewise, the materials were composed of either molecules, basically, or say atoms. There is no exception for this. That means every material that we know in our universe is made up of atoms or molecules. Now, I know that there are school students in this audience. If I ask the questions, who is the first man who prophesy or who predict that material bodies can have atoms? And the answer is none other than Ludwig Boltzmann. And the context in which he said this marvelous, what I have to say, this point is regarding in an effort to understand what is heat. Maybe in school students, at least some of you might have heard that at the very early period. Very early means maybe at the beginning of the 19th century, some 1800s, say 1850 or 1860, that years. People suspect that this heat can be a fluid, right? Just like water. But different from water, this fluid doesn't have any weight, doesn't have any color, doesn't have any other properties like a conventional fluid. This is the basic reason why material bodies having heat. If a body have this fluid, and they named it as calorie, if a body have this fluid, it will be hot. And when you connect two bodies of different temperatures, this fluid will flow from hot bodies to cold bodies. So it flow from hot to cold bodies. And if a material have more content of calorie fluid, it will be more hot. This was the theory regarding heat at that time. But this failed to explain many of the things. One of the things it's failed is, suppose you consider a stone which is falling down towards the ground. When it strikes the ground, it will be suddenly get heated. And according to this theory, if it is get heated, it must receive the calorie from somewhere, or the calorie fluid has been created, right? So when it is coming down and hit the ground, how suddenly this block of material has achieved or attained an amount of calorie fluid that is not explained by this concept. So many people thought that this must be revised, or idea must be revised. It is in this time, around 1865, Boltzmann came forward and said that heat is not a fluid. Instead, it is an energy, kinetic energy. Kinetic energy of what? Kinetic energy of some kind of microscopic structures in matter. And maybe this is the first time where we have a conclusive statement that the matter is made up of constituent microscopic structures. Now we call it as atoms. Okay. So Boltzmann said that the heat that we feel is actually the kinetic energy, or say the random kinetic energy of the atoms or molecules in the material, right? Unless we have this kind of microscopic structures who can carry heat as their random fluctuation or random motion, no material would be able to carry heat. So let me repeat my statement. If any body has to carry heat, it must have an atomic structure. Without an atomic structure, no body can carry heat. So this is the reason that why Boltzmann put forward the atomic theory. So without the existence of microscopic structures like atoms, no material can carry heat. Or we can put the statements that to carry heat, matter must have an atomic structure. And today this atomic structure is very well known to us, even to the school students. Every material consists of atoms, right? This point was actually started by Boltzmann. And you must remember that when Boltzmann made the statements, he doesn't know about the structure of these atoms. He doesn't know the other properties of atoms. He doesn't know that the atom consists of a nucleus, it consists of electrons. Nothing. He just assessed that if a body has to carry heat, it must have an atomic structure or a microscopic structure. And later we identified the various properties of this basic microscopic structure called atoms. These are the known things. Now we know that all materials consist of atoms or molecules. Now we were asking a question which may be highly revolutionary. Well, the material in our universe, we have both matter and space. Of course, time is there. We may call it as a space-time. And you know that matter is consist of, or it has microscopic structures like atoms. Now, do the space-time has got such a structure? Do space-time has got a microscopic structure like matter? This is a very recent question, right? Nobody, I don't think anybody asked such a questions before 20th century, or say 21st century. What is the context in which this question has been asked. Because we know that if any material has to have an atomic structure, it must carry heat, or it must have the capacity to carry heat. Or in other words, we can say that only those bodies who have the capacity to carry heat can have an atomic structure. So when you are saying that whether the space has got an atomic structure, it indicates that the space may have the capacity for carrying heat. Or in more general sense, you can say that the space is hot. Now, when you are saying that the space is hot, it is not the hotness that we are feeling when you are sitting somewhere. That heat is just because of the heat of the surroundings or heat of the atmosphere, right? Atmosphere, there is, we have atmospheres of different gases, and they carry heat. Because of heat, these atomic particles of the atmosphere will execute random motions. And because of this, we experience the heat. I'm not talking about that heat. I'm concerning about the very, very element called space-time, the arena of the dynamics of all the material bodies, right? Does that space-time can have atomic structure? Or in a more general sense, this question is equivalent, that whether the space-time have the capacity to carry heat just like matter. If it have a capacity just like matter to carry heat, then no doubt it must also have atomic structure, right? So to my opinion, this question was maybe first asked and maybe first answered. Maybe first asked, but surely I am confident that it was first answered by none other than Professor Padmanabhan. The answer is that, yes, space has the property to carry heat. Therefore, it must have an atomic structure, right? So the question is, how can space can carry heat? I already told you that the heat of space-time, which I mean is not the usual heat or temperature we are feeling from open space where there is atmosphere, right? And again, I am specifying that the heat of space-time, what I mean is the real heat energy of the very space-time, right? In school days or in school syllabuses, you have studied that we can have a space-time where a three-dimensional space and one-dimensional time. So I am talking about that three-dimensional space and one-dimensional time. Together we can call it as a four-dimensional space-time, right? And I am asking the question, this space-time can have an atomic structure. Do this have an atomic structure? And the answer is yes. And because it can carry heat energy, and we have to follow the theories or the opinions or the discovery of Professor Padmanabhan, that how can a space can carry heat? It's a very revolutionary idea. Nobody has thought about it before. Okay. So with that, let me go to the next slide. So what I have written here is that like matter, space can too have atomic structure, right? If it in Malayalam, പദാർത്ഥത്തിനെ പോലെ തന്നെ സ്പേസിനും കണികാ സ്വഭാവമുണ്ട്, right? So what we are thinking today is how Padmanabhan got this idea, or how Padmanabhan got this discovery, right? The entire thing is relying on understanding gravity. Okay, whether the space has got the capacity for carrying heat, therefore it can have microscopic structures, what we called as the atoms of the space-time. Whether these things are really true, to understand that, we have to understand gravity, right? So I hope I have introduced my initial point. I don't mind if you are asking questions on the way of my talk, but it should be audible, not through the message, right? Let me repeat once more what I'm going to talk, right? All of us know that the matter has got an atomic structure, right? There is another component in our universe called space-time, consists of 3 space and 1 time dimensions. The question we are asking, like matter, whether space is also got an atomic structure. The answer, which is coined by Professor Padmanabhan, is that yes, space can have an atomic structure because it has the capacity to carry heat. The next question is, how can a space carry heat? In order to understand that, we have to understand gravity. Okay, so let me go on from here. I hope I am clear to you. Okay, so we are asking the question, what is gravity, right? So at least some of us may think funny that what is the relevance of this question? If you are asked to any school students, he will say that yes, we know gravity. What is gravity? It is defined by Isaac Newton long back in 1665, that gravity is the attractive force between material bodies. And the law which is very well saying that the force is directly proportional to the product of the masses and inversely proportional to the square of the distance. Well known, right? And this law we are using to understand the orbital motion of the planets, to understand the orbital motion of the satellites like Moon. And we are also using this very same law for projecting artificial satellites into the outer space. So this law has been a triumph regarding its successes. It explained the laws of planetary motion due to Kepler, right? It explained the fact that why the bodies are falling down when you are throwing up in Earth. And it also helps us to launch artificial satellite to the outer space for various purposes. So that is gravity. So for any common man, gravity is a force operating between massive bodies, right? And this law has sustained its until what I have to say, around the beginning of the 20th century. Or to be specific, I can say that say until 1915, the law has sustained without any attack. So nearly 2.5 centuries, the law survived. What happened after that? Maybe school students or also college students came to know that there was something, or there was some situations where Newtonian gravity is or was failed, right? For example, in one of the situations where it failed is predicting the orbital motion of planet Mercury, right? Now, what is wrong in the prediction of the Mercury's planetary motion regarding Newtonian gravity? We know that there are something called perihelion and aphelion. Perihelion is the nearest position of the planet to the sun, and aphelion is the farthest position of the planet to the sun. If you take particularly the orbit of Mercury, as we are seeing in the figure, the orbit is slightly shifting as it revolves around the sun. And Newtonian theory has failed in predicting this correct shifting of the orbits. So let me repeat. The first known drawback of the Newtonian gravity is in predicting the shifting of the orbit of planet Mercury, the very first planet. But you know, this inability was so minute. Therefore, even though this discrepancy was known right from the proposal of the Newtonian theory of gravity, people didn't care about it because it was so minute. It was thought that maybe some observational mistakes may be there, or some slight modifications in the law will cure it. But till now, there was no successful way that we can modify Newtonian theory, or we can check for our observational accuracies. This discrepancy is still there. So, however small it may be, a discrepancy is always a discrepancy, right? So, at least some of the persons lived in that time, during Newton's time, I thought that this may not be the complete theory of gravity. We must go for understand gravity further to make a new law or a complete law which describes gravity completely, right? But the major threat to this very law came in the year 1915. What is the importance of 1915 year? It was the year when Albert Einstein proposed his theory of special relativity, right? What's regarding special relativity so important with reference to the gravity theory of Newton? The major point in special relativity is that nothing can travel faster than a velocity which is equal to the velocity of light in free space. That is around 3 into 10 to the power 8 meter per second. No bodies in this universe. Not only bodies, any interaction, like say gravity or electromagnetic, anything that is being a member of this universe, either it will be a material body or it may be an interaction like gravity or electromagnetism, cannot travel faster than that of light in free space. So there is an ultimatum for the velocity of everything in the universe, right? But when you go to Newtonian theory of gravity, it says that the gravity can move, gravity can propagate, or the influence of gravity from one body to another can propagate with infinite velocity. There is no limit to the velocity for propagation of gravity influence, right? It is traveling with infinite velocity. Its effect is instantaneous. So it comes to know that there is a conflict between special theory of relativity and Newtonian theory of gravity. And these theories to be compatible with each other. People thought that either two choices are there. Either Newtonian gravity is to be modified in accordance with the special theory of relativity, or special theory of relativity is to be modified in accordance with the Newtonian gravity, right? But later it comes to know that the Newtonian gravity is in problem. Therefore, you have to change your idea of gravity or ideas on gravity so that it is to be compatible with the special theory of relativity. ഈ ന്യൂട്ടോണിയൻ തിയറിയുടെ പരാധീനതകൾ കാരണം തെറ്റ് ന്യൂട്ടോണിയൻ ഗ്രാവിറ്റി തിയറിക്കാണെന്നും ന്യൂട്ടോണിയൻ ഗ്രാവിറ്റി തിയറിയെ പരിഷ്കരിക്കേണ്ടതുണ്ടെന്നും എങ്ങനെ പരിഷ്കരിക്കണം? വിശിഷ്ട ആപേക്ഷികതാ സിദ്ധാന്തവുമായിട്ട് പൊരുത്തപ്പെട്ടു പോകുന്ന രീതിയിൽ അതിനെ പരിഷ്കരിക്കേണ്ടിയിരിക്കുന്നു. എന്താണ് പൊരുത്തക്കേട്? ന്യൂട്ടോണിയൻ ഗ്രാവിറ്റിയിൽ ഗ്രാവിറ്റി ഇൻഫ്ലുവൻസ് സഞ്ചരിക്കുന്നത് ഇൻഫിനിറ്റ് വെലോസിറ്റിയിലാണ്, ഇൻഫ്ലുവൻസ് ഇൻസ്റ്റന്റേനിയസിലാണ്. അതേപക്ഷം ആപേക്ഷികതാ സിദ്ധാന്തം അത് അനുവദിക്കുന്നില്ല. There is a limit to the velocity of anything in the universe, right? So in order to resolve this conflict, again there comes Einstein, right? And in a way he combined Newtonian gravity with the special theory of relativity, but the result was a complete revolution in understanding gravity, right? In a sense, we can say that he just combined Einstein's relativity, Newtonian gravity with Einstein's special theory of relativity, but the result was tremendous. What was the tremendous result there? It stipulated that Gravity is not a force as envisaged by Newtonian law. Instead, it is it is the curvature of space-time. So let me repeat my statement. As we thought before, gravity is not really a force between material bodies. On the other hand, gravity is actually the curvature of space-time. Now it comes that to understand this statement is we need little bit thinking, or even some says that we need a little bit of higher mathematics too. But I think it is not too difficult to understand this idea that gravity is the curvature of space-time. So let me try, say, a few minutes for explaining what is actually the gravity theory of Einstein's. It is otherwise called the general theory of relativity. I hope you have seen the screen. Okay. So what we have done here, that figure is slightly distorted. May I make a correction slightly in just a few seconds? Okay, now it is okay. All right, fine. Now it's fine. So you have seen these two figures. A man is sitting on the ground in earth, and another man is sitting in the outer space where there is no material bodies around, no planet, nothing around. And he is inside a chamber. He can't see outside. And his chamber is fitted with a rocket in the rear end. Okay. So watch this figure very carefully. One man is sitting on the ground, and another similar man is sitting on a spaceship uh, far away in the outer space where there is no gravity. Okay. So look at the man on the surface of earth. He is dropping two balls of different masses from the same height. And we know what is going to happen. We know that these two balls, irrespective of their differences in mass, will fall equally fast and hit the grounds at the same time. Okay, let me repeat my statement. The man is dropping two balls at a given height above the earth's surface, and the balls are of different masses, and these two balls falls down equally fast and hit the ground at the same time, irrespective of the differences in their masses. This is a common experience, right? So one may wonder why these two masses are touching the ground at simultaneously, even though their masses are different. That's a property of gravity, that all bodies having the same acceleration under uniform gravity. I hope this point is clear to you. Right? Anybody having any questions regarding any point, may please ask at the right time. Okay. Now coming back to the man on the spaceship, right? Where there is no gravity, right? Why the bodies releasing above the surface of the earth are falling down? Because earth is attracting them. Because there is gravity of earth, right? It is because of that reason these two balls are coming down. They are attracting towards the ground. But assume the situation of the second man where there is no gravity. He is not sitting on the surface of any planet. There is no material bodies around it to produce sufficient gravity to cause these balls to fall down. So in the absence of gravity, if you place two balls at somewhere in space, it will stay there. No movement, no falling, nothing. Why? There is no gravity. There is no gravity in any directions, either downward or upward, nothing. So these bodies will stay there in the positions where they are being released. ഈ രണ്ട് ബോഡീസും എവിടെയാണോ നിങ്ങൾ ശൂന്യപ്രദേശത്ത് വെച്ചത് അവിടെ തന്നെ അതിരിക്കും. കാരണം എന്താ? അവയെ താഴേക്ക് വലിക്കാനായിട്ട് ഇപ്പോൾ ഗ്രാവിറ്റി ഇല്ല. ഓക്കെ. Now assume that the spaceship is accelerating up by connecting it with a rocket in the rear end. Right? So the rocket is going up, say with an acceleration exactly similar to that of the acceleration due to gravity, and that is 9.8 meter per second squared. So what we can think to be happen inside that spaceship, this rocket will accelerated up with an acceleration equal to that of the acceleration due to gravity, and this will go up and hit these two balls simultaneously, and the lower four of the spaceship doesn't mind that one body is of higher mass and the other one is of lower mass. It doesn't have to mind the mass difference between these two bodies. It is naturally going up with an acceleration which is it getting from the outside rocket and hitting the balls simultaneously. But what is being seen by the observer inside the spaceship? He is standing on the floor of the elevator inside, and while he watching the balls, what he is seeing is that these bodies, both the highly massive one and the less massive one, are falling equally fast and hitting the floor of the elevator simultaneously. Right? If an outside observer will see it, he will say that no, the bodies are not falling. What is actually happening is that your lower floor is accelerating up and hitting both these masses simultaneously. But the inside mind will just seeing that these two balls is going down, right? Even though their masses are different, they are going down with equal fastness and hitting the floor of the elevator simultaneously. And he will conclude that this will happen only in the earth where there is gravity. So I must conclude that there is gravity in my frame. Okay. That means that a uniform gravity can be mimicked with an accelerating frame or by an accelerating frame. Uniform gravity നമുക്കൊരു accelerating frame വെച്ച് artificially create ചെയ്യാൻ പറ്റും. Once you create such an artificial gravity, there is no experiment in this universe which can distinguish between a real gravitational field and an mimicked gravitational field with an accelerating ship. No experiment is there. So we could say that these two situations are indistinguishable. ഒരു ആക്സലറേറ്റിംഗ് ഫ്രെയിമും യൂണിഫോം ഗ്രാവിറ്റി നമുക്ക് വേർതിരിച്ചറിയാൻ പറ്റത്തില്ല. They are equivalent to each other, right? Therefore, the statement is that gravity is indistinguishable from acceleration. There is a slight spelling mistake in the word from. Indistinguishable from acceleration. Okay. So what it tells you further, right? Further, suppose you are igniting a torch from one wall of the chamber on the left side, and the torch and the light from the torch beam is proceeding towards the other wall of the chamber. Okay, let me make it clear. You have a torch and you are igniting it from one wall, say for example from the left wall, and the light from that torch is going towards the other wall. At the same time, your spaceship is accelerating up. So while the beam of light, it is traveling with a fantastic velocity of 3 into 10 to the power 8 meter per second. But whatever high this velocity is, it's a finite velocity. It will take a finite time, however small it may be, to reach the other wall. So by that time the light beam reach the other wall, the spaceship is accelerating up. Maybe it's a very minute amount of time, but the spaceship is still accelerating. So the beam will hit the other wall not on the diametrically opposite point, but to a point which is little below the diametrically opposite point. I hope my idea is clear to you. Right? You are igniting a torch from the left wall, and our spaceship is accelerating up. So by the time the light beam reaching the other wall, the space has made some amount of movement in the upward directions. So it is sure that the light beam will not hit the diametrically opposite point. It will hit a point below the diametrically opposite point. That is shown in the third figure. Okay. So this what is being known as the bending of light, right? So this bending of light is happening in an accelerating frame. And we just now say that an accelerating frame and a real gravitational field are equivalent. Therefore, if light is going to bend in an accelerating frame, it must be true, or it must bend in the presence of real gravity also. This was a remarkable prediction made by Einstein. This was not known by Newtonian gravity theory, because Newtonian gravity theory is concerned only about masses. Light is a massless object. So going further from here, you see in an accelerating frame or in the presence of gravity, light will bend. At the same time, we know that there was a principle regarding the movement of light that is given by one of the very celebrated scientists known as the Fermat's. Fermat's theorem stipulated that, or Fermat's principle saying that light will move in straight lines. Let me repeat. Fermat's principle saying us that light will move in straight lines. At the same time, in the presence of gravity, light is taking a curved path. Let me take these two sentences side by side. In one side, I have, in the presence of gravity, light is taking a curved path. On the other side, Fermat's principle telling me that light will take straight path. So what I have to conclude? Now in an accelerating frame, the straight path means a curved path. Straight path means a curved path. Why this curved path become the straight path? It is because the space inside this accelerating frame is itself being curved, is itself curved. Okay. Suppose you are walking along a straight road, the surface of the road is so straight and your path is so straight. On the other hand, if you want to climb, say, a hill, and you climb over the top of it and climbing it on the other valley, your path will naturally be bent, naturally be curved. Why it is that? It is because of the geometry of the hill. The hill itself is a bended object. Therefore, the path is automatically bended. Like that, the space-time inside an accelerated frame or in the presence of gravity will be curved. So every body, whether it is a body or a light or anything, have to make their movement along this curved trajectory or curved space. Therefore, their trajectory will be automatically curved. So the curving of light is not because of the curving of the light itself, it is made because of the bending or curving of the space-time. Therefore, we must conclude that inside an accelerating frame, the space-time will be curved. If that is the situation in accelerating frame, then that is true in the presence of gravity also. In the presence of gravity also, space-time will be curved. So I hope at least in some extent I have communicated this idea that gravity manifests itself as the curvature of space-time. Okay, so this idea is drastically different from that of Newton. Newton says that gravity is mere force between material bodies, but Einstein's propound that gravity is the curvature of the space-time. So in this regard, if you take the orbital motion of planets around the sun, right? When you take the Newtonian theory of gravity, what you will say is that there is attractive force between sun and the planets. Because of this attractive force, these planets will take a circular path, a curved path, right? In the context of Einstein's theory of gravity, what is really happening there is the sun is a huge body. You know, the more than 99% of the mass of the solar system is lying in sun. Therefore, the curvature produced by the sun, by the way, the curvature is produced by material bodies. The curvature produced by the sun is so huge. It is in this curved space that the other bodies have to make their movement. Therefore, their trajectories will be automatically curved. അപ്പോൾ സൂര്യന് ചുറ്റും പ്ലാനറ്റ്സ് റിവോൾവ് ചെയ്യുന്നത് പ്ലാനറ്റ്സും സൂര്യനും തമ്മിലുള്ള ആകർഷണ ബലം കൊണ്ടല്ല, മറിച്ച് സൂര്യൻ സമീപ സ്ഥലകാലത്തിലുണ്ടാക്കുന്ന ശക്തമായ വക്രത കാരണം സ്പേസ് ടൈം വളഞ്ഞു പോവുകയും ആ വളഞ്ഞ സ്പേസ് ടൈമിലൂടെ ശരിക്കും പ്ലാനറ്റുകൾ നേർരേഖയിലാണ് സഞ്ചരിക്കുന്നതെങ്കിലും സ്പേസ് ടൈമിലുണ്ടാകുന്ന വളവ് കാരണം അവയുടെ ഓർബിറ്റ് സർക്കുലറായി പോകുന്നു, വളഞ്ഞതായി പോകുന്നു. ദാറ്റ് ഈസ് ദ റീസൺ. അപ്പം നമ്മൾ ഇവിടെ ഓർക്കേണ്ട പ്രധാനപ്പെട്ട പോയിന്റ് എന്ന് പറയുന്നത്, ഗ്രാവിറ്റി എന്ന് പറയുന്നത് ഒരു ഫോഴ്സ് ആണെന്നുള്ള തെറ്റിദ്ധാരണ നമ്മൾ ഇതോടെ മാറ്റണം. ഇറ്റ് ഈസ് നോട്ട് എ ഫോഴ്സ്. Then what is it? It is the curvature produced on the space-time by the presence of matter or energy. Okay. അപ്പോൾ ന്യൂട്ടോണിയൻ തിയറിയെ അപേക്ഷിച്ച് വളരെ റെവല്യൂഷണറി ആയിട്ടുള്ള ഒരു ഐഡിയയാണ് എന്താണ് ഗ്രാവിറ്റി എന്നതിനെക്കുറിച്ച് ആൽബർട്ട് ഐൻസ്റ്റീൻ്റെ ഗ്രാവിറ്റി സിദ്ധാന്തം അഥവാ പൊതു ആവേശികത സിദ്ധാന്തം, ജനറൽ തിയറി ഓഫ് റിലേറ്റിവിറ്റി പറയുന്നത്. ഗ്രാവിറ്റി ഈസ് ദ കർവേച്ചർ ഓഫ് ദ സ്പേസ് ടൈം. അപ്പോൾ ന്യൂട്ടോണിയൻ തിയറി വരുന്നത് 1665 ഇൻ 1665, ആൻഡ് ഇറ്റ് വാസ് സർവൈവ്ഡ് അണ്ടിൽ 1915. So nearly 2.5 centuries. After 1915, the theory of gravity was Albert Einstein's theory of gravity, that is the general theory of relativity. And it predicted many things which was not known by the Newtonian theory. For example, bending of light. It predicted things like black holes. It can use it to understand the dynamics of our universe, nature of our universe. ഇത്തരം കാര്യങ്ങളൊന്നും നമുക്ക് ന്യൂട്ടോണിയൻ ഗ്രാവിറ്റിയിൽ നിന്ന് കിട്ടത്തില്ല. ന്യൂട്ടോണിയൻ ഗ്രാവിറ്റി പറയുന്ന ഓർബിറ്റൽ മോഷൻ പോലെയുള്ള കാര്യങ്ങൾ വിശദീകരിക്കുക മാത്രമല്ല, അതിൽ കൂടുതലായിട്ട് പുതിയ കാര്യങ്ങൾ പ്രഡിക്റ്റ് ചെയ്യുകയും അവ ശരിയാണെന്ന് കണ്ടെത്തുകയും ചെയ്തു. സോ ദാറ്റ് ഇസ് ദ ട്രയംഫ് ഓഫ് ഐൻസ്റ്റീൻസ് തിയറി ഓഫ് ഗ്രാവിറ്റി. And this theory is there even now, right? Now it is, I think, more than 100 years have passed, right, since the birth of Einstein's general theory of relativity, theory on gravity. And almost all the scientists or the whole world believes that Einstein's theory is the right theory of gravity. What is the theory? Gravity is nothing but the curvature of space-time. And who produced the curvature? Mass or energy. Higher the mass, higher the energy, curvature will be less. Okay, so there is no attraction, as said by Newton, between matter particles. Okay, So I think so far it is clear to you. If any questions at this stage can be asked, otherwise I have to go to the next stage. Okay. So we have so far two theories of gravity. One is Newtonian theory of gravity, that is somewhat outdated. And second, we have Einstein's theory of gravity, that is still surviving as the more correct theory of gravity. Now one can ask the questions. Is Einstein's gravity is complete? Does it have any drawback? Did we understand the gravity in the most correct way? Well, why we are asking these kind of questions? Or do we suspect that even Einstein's theory have some drawbacks, just like Newtonian theory have drawbacks in the early times? Well, to that question, the answer is yes, there are some drawbacks for Einstein's theory of gravity too. And one of the major drawback is that it is not being unified with the second revolution of 20th century called quantum mechanics, right? Why it is being a drawback? Because Einstein's theory of gravity and quantum mechanics are two independent theories. And why you are saying that the gravity theory is not complete unless you make a unification of it with the quantum theory? Well, quantum theory deals with minute particles or atomic particles, correct? Now, while you come to gravity, when the intensity of gravity is very, very high, right, you must combine it with quantum mechanics. Otherwise, we can't able to study or understand the properties of gravity when the gravitational influence is so high. For example, you want to understand black holes, where the intensity of gravity is too high. You can't understand such a situations without unifying gravity with the quantum mechanics. Or suppose you want to understand the early stages of the expansion of our universe, right? You have to unify Einstein's gravity theory with the quantum mechanics. Without that, you can't study the early stages of the universe, right? This is the fate of any theory of physics. So you take electromagnetic theory, right? Electromagnetic theory should be combined with the quantum theory in order to study the real dynamics of the microscopic particles like electrons and protons, etc. And we already combined it. The combination of this is what we call as the quantum electrodynamics. But such a approach, combining Einstein's gravity with quantum theory, has not been become a success till now. Or I can say that combining Einstein's gravity with the quantum mechanics is failed so far, right? So this is the major failure. Maybe one can consider it as the failure of quantum mechanics, or even one can consider it as the failure of Einstein's theory of gravity. In both way you can go. But all indications are along the direction that there is something wrong with Einstein's theory of gravity. So without going into further explaining what are the other failures of Einstein's theory of gravity, let me make the statement that Einstein's theory of gravity has some drawbacks, right? I'm not saying many drawbacks, but has some drawbacks, very severe drawbacks. And the major among them is that it cannot be combined properly, or we failed to unify Einstein's gravity properly with quantum mechanics or quantum theory. This means that we are somewhat far away in understanding really what is gravity. Okay, so that means that we still have to go further. Maybe we need a new law other than the law given by Einstein, right, to understand or to describe gravity. This is not, the fate of gravity is not being shared with other forces. Maybe only this gravity force has been undergone many revolutionary things in the history of the mankind. Okay, so I will now concentrate on how we can remove or bypass this drawbacks of the Einstein's theory of gravity, so that we can safeguard the theory, or even we can go for a new theory. Okay, so here comes uh, uh, the footsteps of Professor Padmanabhan, right, in a way to modify our present idea regarding gravity. Now, before that, I have to go to tell you a very, very important discovery that was made around the year 1975 by two peoples, Davies and Unruh. Even this is, I have to say, that a completely theoretical discovery. Why theoretical discovery? Because we are unable to prove it by conducting any precise experiment. And I will tell you why. Right. Davis and Unruh, two people, independently showed that if any observer, anybody, running through the space-time or through the space with an acceleration, then the space will become hot to him. Let me repeat my statement. For any observer who is accelerating, not merely running, is accelerating, running with an acceleration through the space, then he will feel that the space-time is hot. Again, I want to remind you that this hotness of the space-time is not something the common hotness of the space we are feeling in the presence of atmosphere. This is the unique hotness of the space-time, irrespective of the presence of atmosphere. So the statement and their proof is that if you run with an acceleration equal to gravity, say g, you are running with an acceleration g equal to 9.8 meter per second squared through the space, and you are carrying a thermometer which is so precise and so meticulous in such a way that it can measure any minute temperature. If you run with such an accelerations, then your thermometer will show that the space-time has got a temperature. Now, unfortunately, if you run with an acceleration equal to that of gravity, say 9.8 meter per second squared, the calculated temperature is around 10 to the power minus 30 Kelvin. 10 to the power minus 30 Kelvin. And we know that we don't have any apparatus or any mechanism by which or using which we can measure this very tiny temperature. That is why I told you in the beginning that this is a theoretical discovery. But the theory and the calculations they have used is the most modern field theory, and no way we can suspect their calculations or their predictions. What we can blame is our own capacity for making a precise measurement of such a low temperature. So we must accept the fact that anybody who is running with an acceleration through the space will feel that the space-time or the space is hot. Okay. Now you must remember that an accelerating frame or an acceleration is equivalent to gravity that I have told you before. An accelerating frame and gravity are one and the same. So when this man is running through the space-time with an accelerations, it is equivalent to a gravitational field. It is in that field we found that the space-time is hot. Therefore, the hotness of the space-time or space and the gravity, because the man is accelerating one, and the gravity has got a very strong connection. right? The accelerating man is equivalent to gravity. And he feels that the space-time is hot. So we can say that wherever there is gravity, the space-time will be hot. Let me make this description once again. The effect proposed by Davis and Unruh, popularly known as Davis-Unruh effect, says that an accelerating observer will feel that the space-time is hot, and the temperature he measures is proportional to his own acceleration. But an accelerated frame is equivalent to gravity. Therefore, what we must conclude is that in the presence of gravity, the space-time will get hot. Right? So space-time is getting heated. If you run with an increased acceleration, the intensity of gravity will be high, and the temperature of the space-time will be more high, and the space-time will be carrying more heat. So there is a strong connection between gravity and thermodynamics. Thermodynamics is dealing with the heat and temperature. Gravity is dealing with the curvature of the space-time. These two are intimately related. This is the prediction made in 1975, but this was quite unnoticed. And this was some way noticed or resurrected after the discovery of Professor Padmanabhan. And what he has shown that the Einstein's equation of gravity, right, just like Newtonian law, believes that there is an equation for gravity which was proposed by Einstein. And that very particular law can be reframed as a law of thermodynamics. This was an astonishing discovery, a profound discovery, a very striking discovery that gravity equation put forward by Einstein is mere a thermodynamic law. Nobody knows until that time that the Einstein equation was a thermodynamic law. What does it imply? The moment you understand that Einstein's gravity equation is thermodynamics, we know that what is Einstein equation says? It says that the space-time is curved because of presence of matter. And that curvature, we are calling it as gravity. And if this space-time is hot, means gravity and thermodynamics, or the geometry of the space-time and thermodynamics are intimately connected. Right? So in one side, you have Einstein's theory saying that gravity is the curvature of the space-time. On the other side, you are come to know that Einstein's equation are nothing but thermodynamics. Or when you say that it is thermodynamics, you must believe that the space-time is hot or it must have a temperature. Thermodynamics is always dealing with the hotness and heat amount. So there is a duality between curvature and heat content of the space-time, right? So going one step further, he postulated that the very same gravity which you have described using Einstein's theory of gravity is nothing but the thermodynamics of space-time. Let me make my statements one more. Gravity of the as made by Einstein's theory, that the gravity is the curvature of the space-time. You can also say that gravity is the thermodynamics of space-time. I hope this point is clear to you, right? So the new slang made by Professor Padmanabhan is that gravity is actually the thermodynamics of space-time. Means the space has got the capacity of carrying heat. It must have a temperature. Where this idea is coming from? It is from Einstein's equation itself. How do you understand that? You can easily rewrite Einstein's equation into a thermodynamic law. Who did it? It is did by Professor Padmanabhan. This you have to combine with the earlier discovery of Unruh and Davis, that whenever you run with an acceleration, you will feel that the space-time is hot. And this one is equally similar to that. When you are running with an acceleration, you are an accelerating frame. Accelerating frame is actually gravity. And you are saying that the space-time is hot. So what Professor Padmanabhan did is a similar thing, which was done in some other way by Davis and Unruh. Padmanabhan actually restructured the Einstein's equation of gravity into a thermodynamic law. Reveals that gravity is really the thermodynamics of space-time. Once you believe that, then you must accept that the space-time, just like matter, can be hot and it can possess temperature. Right? Then you go back to the very statement of Ludwig Boltzmann. If a substance can carry heat, it must have a microscopic structure. Can you enumerate the number of microscopic structure in a material body? Yes, I can. I can use the principle proposed by Ludwig Boltzmann. If I divide the total energy of the body with the temperature, say half kBT, E by half kBT, this is known even to the school students up to maybe from 8th standard onwards. You take the heat energy of any material body and divided it with the half kBT. It was something we study it as, say, equipartition theorem. Okay, you divide the energy with the half kBT, you will get the number of atoms. When Boltzmann proposed this equation, he doesn't know the details of the atoms or details of the molecules, but he could able to count the number of atoms in the space, in the material body. Just like why did he propose this equation? Because he proposed that if a material can carry heat, it must have a microscopic structure. Just like this, Professor Padmanabhan revealed that since the space-time is hot, Einstein's equation is a thermodynamic law, then it has got a temperature. Then you can say that space-time must have a microscopic structure. Otherwise, it cannot carry heat. And we call this microscopic structure as the atoms of space-time. Okay? So the idea that atoms of space-time do exist is because of the realization that space-time is hot. How do you know that space-time is hot? Because gravity means the thermodynamics of space-time. How do you know that gravity is the thermodynamics of space-time? The very Einstein equation is nothing but the law of thermodynamics. Right? Then you can ask further, do you able to enumerate how many number of atoms are there in certain volume or certain area of space-time? Yes, there is an equation that is given by Professor Padmanabhan. Unfortunately, that slide is not there, but I will tell you how. Okay. We want to calculate the number of atoms in space-time, right? You should take an area, any area, right? Say 1 square centimeter area of space, 1 square centimeter area of space. And you are asking the question, how many atoms of space or say space-time are there? Then the answer is, you divide this area with Planck area. Planck area. Planck area means the basic area in quantum mechanics. Below that, nobody can probe. It's a minimum area. And the length corresponding to it is the Planck length is the minimum length. So you take the Planck area, it comes around 10 to the power minus 70 meter square. Right? So you take 1 square centimeter of the space and divide it with the 10 to the power minus 70 meters square, then you will nearly get 10 to the power 66 atoms are there in 1 square centimeter, right? So this formula is something different from the formula for matter which was proposed by Boltzmann, where he proposed that you divide the total energy with half kBT. And here the definition is slightly different, right? You divide the area of the space-time with Planck area, you will get the number of atoms. Then one may suspect why you are dividing the area instead of taking, you are not taking the volume, right? There was a result in quantum mechanics that in the microscopic level, this may be beyond our reach. In the microscopic level, the dimension of the space-time is 2. Or in short, dimension of space is 2. So what we are trying to enumerate is the number of atoms in the microscopic state. Therefore, you should consider it is a two-dimensional thing at the microscopic level. Therefore, instead of calculating the number of space atoms, you have to take the area and divide it with the area of one microscopic unit. And the area of one microscopic unit is Planck area, 10 to the power minus 70. So we want to calculate the number of space atoms in a unit area. You have to divide with 10 to the power minus 70 meter square, and you will get it as 10 to the power 66 atoms in a square centimeter, right? So this idea of discovering that space-time has got a microscopic structure, and you can enumerate the number of microscopic structure just like Boltzmann did the enumeration in the case of matter. So let me say that Padmanabhan is almost similar in the position of Boltzmann. When Boltzmann made the statement that material has got microscopic structure, you can count the number of microscopic structure. He doesn't have any idea about atoms or molecules. Likewise, Padmanabhan today give us a prescription to calculate the number of atoms of the space-time in a given volume or area. And of course, we don't have any idea regarding what is the actual nature of this microscopic structure or atoms of space-time. Does they also have other microscopic structures just like our material atoms? These things are yet to be known or yet to be revealed. But the idea that if you take gravity as the thermodynamics of space-time, that is also a contribution from Professor Padmanabhan, right? Because Einstein's equation is nothing but a law of thermodynamics, then you should believe that since Einstein's theory is regarding the curvature of the space-time or say geometry of the space-time, then if you are believing that gravity is thermodynamics, then the space-time has got thermodynamic properties. And thermodynamic properties are heat and temperature, etc. Therefore, the space-time is hot. Just like Boltzmann said, if it is hot, it must have a microscopic structure. That's all said by Professor Padmanabhan. And he gave us a formula for calculating the number of microscopic atoms or atoms of space-time, right? So this is my key point. Time to stop here. So let me conclude that 2 points. We have to go ahead in understanding what is gravity is. The first law of gravity given by Isaac Newton in the year around 1665, some 300 or more years back, and he postulated that gravity is the attractive force between bodies having inertial masses, and that idea has been changed in the year 1915 when Einstein postulated that gravity is not really the force, but it is the curvature of the space-time. Around the year 2002, Padmanabhan showed that gravity is actually the thermodynamics of space-time. Therefore, it has the capacity to carry heat and temperature Hence, it has got a microscopic structure. And you can calculate the number of microscopic structure using the formula area divided by Planck area. Thank you. I'm stopping here. There are any questions, I may be happy to address.
I think we were very fortunate today to get a talk on Padmanabhan and the atoms of space-time from Professor Titus Mathew. It's a wonderful talk, a talk which keeps the listeners attend every moment of the talk. And I was glued to my system without any gap. So absorbing, so thought-provoking, so deeply involved, postulation of theories which are exciting for any student on science, more so on physics. So we are very, very fortunate. Our students who are listening, they must have been attentively doing. I was just watching. We have not got any dropping out of the number of students who participated. They continue to remain so. At three itself, we had something like 30, and even at four also, we had 30 students attending, in addition to others. And it shows how absorbing and how serious, how good the talk has been. So it's a beautiful flow. The talk had also a beautiful flow and an excellent slide. Excellent slides were there. So the whole thing is articulated so well. Discuss something like a discussion. It is just a very, very beautiful flow it had. Although it was a talk by Professor Titus himself, but I could see a lot of life in it, something like a discussion and of various discoveries. So it's a very, very nice thing. Thank you very much. I want the time to be utilized fully by our students by talking. And I also request if Jayaraman is there, Dr. V. Jayaraman is there, kindly put in a word of what is your appreciation about this talk and how you think it is useful to our students.
Thank you. Could you are able to hear me?
Yeah, we are able to hear you.
I think I should first compliment Professor Titus. I think I have not heard any talk like this in the recent times at all. And the students working under him should be really lucky to have a professor who is able to link the fundamentals properly one to another and leave let us to what they have today and forcing a question to the students how to go about in the future. I think starting from Boltzmann, coming through Newton, and then going to Einstein, Davy through Andrew, and then coming to Padmanabhan and bringing with the beauty linking quantum mechanics to gravity to finally coming to the thermodynamics, linking Boltzmann to Padmanabhan. I think we have got Padmanabhan on par with Boltzmann, much more than Boltzmann. Somewhere our country did not recognize Padmanabhan the way he deserved. And I hear the Professor Titus brought beautifully, and I'm sure the students would enjoy it. I, for myself, I tell you, I am a physics student. I have read all these stories, but linking each one of them and in a way communicating to the general student community, because very, very difficult. In fact, Professor started telling about explaining the space-time curvature, gravity, how it is defined, how mathematically or even physically explained to the students is very tough. I think he explained beautifully, but I have not heard anybody talking like this. Congrats, Titus sir, and I'm sure the students will be most benefited, and I'm going to see some more Padmanabhan coming out of these students to take a flag out of further explore the atom. You mentioned about the space-time atomic structure, and somebody else will start working on that henceforth. Thank you, Professor. Thank you very much.
Thanks, Dr. Jairam. Dr. Jairam is a remote sensing veteran of ISRO, a top-class remote sensing person, and who was a leader, great leader of ISRO. He led the National Remote Sensing Center, Hyderabad, as its director, and has been in Earth observation systems leader in ISRO. And thank you very much.
Thank you.
Thank you.
So what did you say when you come?
Any question?
No, it's all quite clear and I understood most of it.
Varun, any of your students? Hello? Varun?
No, Titus sir. I think it's really initially when you were talking about, I was just thinking, okay, it will be sort of revolution in the thinking of Einstein's gravity theory, because we are being that is what we are using. All our spacecraft operations are our rocket equations, or even planning for our interplanetary missions and all. The problem, thing is, whatever we have used gravity as a force, and then we were doing all these things. But today, I think now we have to have a rethinking of the theory behind what really gravity is. Now you have given us another kind of rather a theory that it is being seen in association with thermodynamics, as our Dr. Jairam sir has put it. It's just earlier we were reading some articles about Einstein's theory. They were disputing, and a lot of course, always in a scientific community, yes, we will always see some kind of discussions going on. But really linking this with a kind of closely linked relations you were being brought out. It was really interesting. In fact, I am interested in reading some more articles related to this. Anyway, I will contact Sajil sir and get some of the links and then try to read and then try to understand the things. But today, I think the understanding, or rather about the gravity and the kind of viewpoint looking at it is now totally getting changed. And then, as our Dr. Jayaraman sir put it, somehow our Indians rather findings are not yet been taken by the world people so easily. I think with your guidance, our future generation students will come out, and definitely I am sure we will come out and then saying that Padmanabhan sir's theory he will be accepted. Thank you so much for your elite talk, but at the same time, you have given so nicely, and then without going into too much of technical jargons, you have explained. It was very nice, sir. Thank you so much for your all the very best. I hope the students are really benefited, and they are lucky to have. In fact, me too. In association with you all, I too got some insight into this. Thank you very much, sir.
Thank you, Sundaramurthy sir, for your valuable comments regarding these things. And this talk is kept in our YouTube channel as a repository for our students and future for future information and knowledge. That's why. And it's a forum we can discuss it more. Is there anybody, any of our guests can?
I think
talk?
Shajil Marsh,
Okay,
is Bhatt Saab is there? PJ Bhatt?
Yes, sir.
Is he available? Bhatt Saab?
What's up? Sir, WhatsApp is not there, sir.
I think he left it. Looks.
Yes, sir. Yes, sir. We have teachers and students. Anybody can join and self-introduce and talk, make a comment on this. We have enough time today, and we are about to finish. Is there anybody who want to speak?
Any questions? Any doubts? Any discussion you want to make? Any point you want to make?
Mr. Kutti, I have one suggestion.
Yes, sir.
Yes, please. Yes, please, Jay.
I think, I don't know about Professor Titus earlier, whether he has written any book on this, because a fundamental book linking all that parameters what he mentioned about, starting from Boltzmann to go through the Einstein and then coming to Newton to Einstein to Davis, and then coming to Padmanabhan. A book what he talks about, written in 40-50 pages, simple Malayalam or in English, whatever it is possible, will be a really enlightening thing for all the students across the country. I think it will be a good effort by him. If not done already, at least a monograph will be made by him for all people to make use of. Thank you.
It's a good suggestion, sir. Great suggestion. I think Dr. Titus will take it as it's in a positive way, and we expect for such a book from his part.
In fact, such a book. In fact, such book will be shortly published by the CUSAT publications.
Very good. Thank you.
Oh, excellent.
Sir, it is excellent. In fact, we are all eagerly looking forward to have that book.
Yeah, it is on the way of publication.
Oh, very good. Very good. So Shajil Marsh, kindly follow it up, and I think we will buy a few copies.
Today we have finished. We have completed our task within our time because of this the time arrangement and the sequence arrangement of concepts by Dr. Titus, sir. And one more thing we want to acknowledge here, and we had a space camp at CUSAT in the 9th or during the Space Week, 9th and 10th of October. It was hosted by these CCs and Department of Physics also. And Titus sir have made a lot of help for us and arranging a Skywatch session by Dr. Shaji. All these things was done with the support of Dr. Titus, and CUSAT is Cochin University of Science and Technology is so helpful and beneficial for our students, especially for the US Space Group. We are acknowledging our thanks in this time also, sir. Then, sir, let's conclude, sir. Yes, sir.
Okay,
Yes,
Shajal Mash. I
yes.
think we can
Then it's time
Thanksgiving
of
and
vote of
conclusion.
thanks, and we thank for the thanks from our whole, from our bottom of heart to the Dr. Titus Mathew for coming and giving a wonderful lecture for our student. It was fundamental science lecture. It's a connecting one, and it's an evolutionary one. It also shows the nature of science. The science, the knowledge is changing. We are updating from basic knowledge, and the new knowledge will be updated by next time. That's happening there, and we are remembering the great scientist of India, Dr. Padmanabhan, also here, and we express our gratitude on behalf of US Space Club to Dr. Titus Mathew and CUSAT on this occasion, and we express our thanks to all the veteran scientists, V. Jairam sir, T.K. Sundaramurthy sir, and E.K. Kuti sir, the founder of this US Space Club, and all the students and who are there. And we have this talk with us in our US Space Club YouTube channel. And we thank you all having with us. And Titus sir, once again, a heartful thanks to you, sir. Thank you for supporting
Thank
us.
you. Thank you. So I can leave, right?
Thank you, sir. Thank you.
Okay.
Thank you
Thank
very
you.
much. Thank you, sir. Thank you.